now, the last talk before the break will be ionization gas dynamics modeling and X-ray spectra calculation of wind bubbles around massive stars with Vikram Dwarkadas giving the talk. Go ahead, Vikram. And I'll shout you out at 9 minutes. We're not hearing anything. Vikram, we can't hear you.
Okay, can you hear me now?
Yes.
Hello?
Yes.
Sorry, I'm not sure what was going on. Okay, I'm talking about ionization gas dynamics modeling and X-ray spectral calculations of wind bubbles around massive stars. And I think I'm having a lot of problems, but anyway. So we're here because we know massive stars lose a lot of mass throughout their lifetime via winds, and at the same time, they also have a large number of ionizing photons that will ionize the surrounding medium. And both of these effects have to be dealt with at the same time. So the interaction with the surrounding medium creates large ionized wind-blown cavities surrounded by a dense shell, which we call as wind-blown bubbles. As the star evolves through various stages, the stellar parameters change, affecting the bubble structure. And when the star explodes, the resulting shock wave also will expand within this bubble. And the supernova evolution and emission from supernovae is decided by the structure of this bubble, and therefore it's important to know it very well. This is something that we really learned from supernova 1987A. So using an ionization gas dynamics code called Avatar, which I wrote with a colleague of mine, Duane Rosenberg, we compute the structure and evolution of the wind-blown bubbles around massive stars. I think many people have done similar work, but I think only Tonia and Arthur, who did some very nice work, and this work actually treated the ionization and recombination carefully, as I will show you in a minute. So we study the time evolution, the dynamics, the hydrodynamics, kinematics, and ionization structure. And then using the ISIS package from MIT with an unfortunate name, we compute the X-ray spectra of the bubbles and compare to observations. So I'm just going to jump into it. Okay, so basically this is a simulation, a spherically symmetric simulation to start with of a wind-blown bubble around a massive star. This red line is showing you the density structure. This blue line is showing you the ionization fraction. This scale on the left-hand side is the log of the number density. On the right-hand side is basically the ionization fraction. 1 is fully ionized. This is almost neutral. Okay, this is the time in years, and the x-axis is basically an expanding grid. So as the shock expands outwards, the grid expands with it. So you will see the grid expanding. Okay, so if we let this run in the main sequence stage for a certain amount of time, and I will stop it here, and you get the basic structure of a wind-blown bubble. So near the star, you have a freely expanding wind. If the mass loss rate and wind velocity is constant, you basically get a 1/r² structure. You have a wind termination shock. You have a low density, high pressure, and therefore high temperature region that we call the shock wind bubble. This region out here is basically an ionized region, like an H2 region. It's formed by the ionizing photons from the star. If you have a large number of ionizing photons, then you have a contact discontinuity and the outer shock, which is more or less radiative. As you can see, this is the ionization fraction, and the ionizing front is basically stuck in the dense shell. So, and this happens quite a bit. You know, the ionization front is stuck in the dense shell. So part of the dense shell closer to the star will be ionized. The rest of it might be neutral. Okay, so we let this run. In this case, in the main sequence stage, it lasts for about 4.3 million years. And you can see that the structure is more or less self-similar. It's not changing shape, even though it's increasing in size. Okay, so we let it go for about 4.3 million years. And then the star is going to become a red supergiant star. Now, in the red supergiant stage, the wind velocity is much lower. The mass loss rate may be a little bit higher. But since the wind velocity is 2 orders of magnitude less, the density goes up by more than 2 orders of magnitude. And also, it creates a new pressure equilibrium. The other point is that the star is much lower temperature, 3,000 to 5,000 degrees. So it cannot ionize the medium. And so the ionization fraction will fall. As I'll show you in the 2D simulations, this falls to almost like 20%. And this is important to simulate when you want to capture the X-ray emission. Okay. So if we let this go into the red supergiant phase, and now I'm going to go much slowly out here, you can see that a new pressure equilibrium is established and the ionization fraction falls. So this region is now much lower ionization fraction. The rest is still fully ionized. And then as it becomes a Wolf-Rayet star, the Wolf-Rayet star momentum will carry the supergiant wind out, it will break it up, and it will ionize the rest of the H2 region again. So now the region is fully ionized, or as much ionized as it can, depending on the lifetime of the Wolf-Rayet stage. And so at the end of the Wolf-Rayet stage, it mixes up this material and it ionizes this region. Okay, so that was the basic idea in spherically symmetric simulations. I want to show you also like 2D simulations. Now in this 2D simulation, you're seeing the density structure. So again, this is the density, here is the time in years, the scale is the log of the number density, and the grid is expanding. So if I let this run for a certain amount of time in the main sequence stage again, as you will see here, I'll stop it here. Okay, so you have a similar structure. You have a freely expanding wind termination shock. This blue region is the shock wind region. This orange region is the H2 region, or the ionizing region. And then you have the dense shell. The dense shell is actually unstable. This is due to ionization front instabilities in this case. And these instabilities are pretty similar to what you see in galactic ionization fronts, for example. The contact discontinuity is also stable, and this is due to more like Rayleigh-Taylor kind of instabilities. So you have various instabilities also occurring in the interior. You can see clumps being broken off and mixed into the interior. So it's not exactly self-similar, of course, but the shape, but the structure remains the same throughout the main sequence stage, as you would imagine. So you have this freely expanding wind termination shock, which is changing in shape and introducing vorticity, and you have the wind bubble. So this goes on for the main sequence until you get to the red supergiant stage. Again, at 4.3 million years, you'll come to the red supergiant phase. So right here, now you get a red supergiant wind coming out. This obviously has a very low velocity. It doesn't go very far. But then you'll have the Wolf-Rayet wind coming out. The Wolf-Rayet wind basically mixes up the red supergiant wind, as you can see now, and it breaks up the red supergiant shell, mixes it up with the surrounding medium. It also ionizes the medium, as I'll show you in the next stage. So now you have this Wolf-Rayet wind coming out. Some of the medium will be ionized, and it also creates all these clumps and filaments. This is important. These things are formed pretty late. They're not fully ionized, as you'll see in the next stage, and that's important for the X-ray emission. Okay, so let's go on to, oh, sorry. This is the similar, but this is showing you the ionization fraction. Ionization fraction of dark red is fully ionized. The blue is neutral. In most of the simulation, you'll see that it's mostly fully ionized, except in the red supergiant stage, where it goes from fully ionized all the way to about, about say 15% ionized or so. And so you'll see it recombining. And that's very important to simulate. And that will again affect the X-ray emission. Okay, so we let this go on for some time. This is the main sequence phase. You can see that it's fully ionized. Some of the ionizing photons are actually leaking out from the shell, as you can see, leaking out from the bubble. This goes on for about 4.3 million years. Then you'll come to the red supergiant phase. And in the red supergiant phase, the star is low temperature. So all this material in the H2 region begins to recombine, as you can see. So this will recombine, and it recombines for some time. And you can see that it's going all the way from this red all the way to this dark blue. So you're basically getting about 15% or so ionization fraction. Then you get the Wolf-Rayet phase, and the Wolf-Rayet phase again breaks up the red supergiant shell, and it also reionizes everything, as you can see out here. So it's all beginning to reionize again. And you can see these various clumps which are forming. Now, these clumps, again, are not fully ionized. As you can see, they're partially ionized, or some of the regions are at least neutral. Again, this kind of dense, partially ionized, the neutral regions can absorb the X-ray emission. So it makes a difference to the X-ray emission.
3 minutes left. Vikram, 3 minutes left.
Thank you. So it's good to understand this carefully. The last simulation the last simulation, this kind I want to show you is basically density contours over the velocity vectors. And the only reason I want to show you this is to show you the kind of turbulence in the bubble. So you can see that as you let it run, you start off with a spherical symmetric wind, and now you have all this vorticity being introduced due to the inner wind termination shock, which introduces the vorticity because the shock structure is changing in size and shape. I'm not going to go into details, and I'll just run through it quickly. You also have to be careful with this because 2D turbulence is different from 3D turbulence in the sense that the energy cascades to higher scales rather than 3D where the energy cascades to lower scales. But you will get this turbulence also in 3D because the reason is still there. It just might not be the same amount of turbulence. But so it's important to note this. Okay, so finally, and I don't have much time left, but what I'm going to show is that we actually calculate the X-ray emission from these. So here is the X-ray emission from one of the Wolf-Rayet bubbles, the observed X-ray emission. You can see it's a very low temperature spectrum. Here is a more recent one from Jesus Tuala, who's done the simulations as well as some very nice observations. Again, a very low temperature spectrum for NGC 6888. So we calculate the X-ray emission from each zone and then total it up together. We use the ISIS package. We use the V-Mikal model, convolve it with the CHANDRA response. We assume a 1.5 kiloparsecs distance integrated over 50 kiloseconds with a certain foreground absorption. I won't go into details. We basically calculated for every time step. And here you can see the density structure, and here you can see the X-ray emission calculated. So you can see how the X-ray emission is varying with time. You may also notice that the X-ray emission, the intensity in the main sequence stage is very low, and then it actually increases as you go up to the Wolf-Rayet phase because you're adding more mass in the same volume. Okay, so basically, if you look at the X-ray spectra, here are spectra from the main sequence phase, here are spectra from the Wolf-Rayet phase, and you can see that they are basically varying in time. This is in the Wolf-Rayet phase, and these are the kind of spectra you get. Now, if you compare these spectra to the observations, and these are two observations from Yu Shu et al. In 2006. This is NGC 6888. This is S308. This is the spectrum from one of our simulations in the Wolf-Rayet stage. This is another one. This is early on. This is slightly in the intermediate stage. And you can see that these spectra, this one compares very well with this. This one compares very well with this. We get the very low temperatures and we get a very low intensity spectrum, which is what you would expect. And this is what you would see. So I don't have to go into the details of why, basically. I will just end out here saying that we do get the nice X-ray spectra and they compare well with their surroundings. So we have developed a code. We can reproduce both the hydrodynamics and the ionization structure. We compute the structure and evolution of nebula around massive stars of various masses. For a 40 solar mass, we show that the X-ray emission in the main sequence phase is too weak to be detected. I didn't go into this. It's higher in the Wolf-Rayet phase. And this is in agreement with observations. And with that, I will end and take your questions and discussion. Thank you.
Okay, do we have any questions? You can raise your hand, or I'm looking in the Slack channel.
I see a hand raised.
Where?
Oh,
okay.
It disappeared. I think that was Jesus. But
I think that was
Jesus?
a clap.
Oh.
I was just clapping.
That's a good thing. It's good to clap.
There's another one.
Gil, here we go. Garcia Segura.
Yeah, Vikram, can you tell me a little bit about heat conduction? Is important or is not important anymore?
We did not add heat conduction in this at all, and we didn't find that we needed to. So, in fact, one of the things I didn't mention, Tuala and Arthur did simulations with heat conduction. We did simulations without heat conduction, but the X-ray spectra look actually very similar. And I think that heat conduction is not important. There is, however, a similar effect because, and I didn't talk much into it, but if you look at, if you go to this simulation, you see that there is a lot of mixing of some of this higher density stuff into the interior, right? So in a sense, you're getting a lot of mass mixed from this. It's not as much mass, maybe, I don't know how much you get through the heat conduction, but you do get mixing of material from the higher density stuff into the lower density interior.
Thank you.
Okay, one more question and then we want to take our break. So Jesus?
Yes, I can complement that to a little bit about the Guillermo's question. Yeah, as soon as you have the instability, so this is what it plays a similar role and similar to the heat conduction. The only difference is that when you include heat conduction is that the luminosity, the X-ray luminosity increases. But even without heat conduction, you reach luminosities very similar to what we observed with observations.
Yeah, I didn't show the luminosity. We did calculate the luminosity. It was, I mean, this is for a specific 40 solar mass star. Those Wolf-Rayet Nebula may not be 40 solar mass stars. It was somewhat smaller than what is observed. Maybe you're right that if you include heat conduction, but it was comparable in sort of, order of magnitude. So I wasn't too worried because we didn't try to tune our parameters to those nebula. We just took a certain simulation and calculated it. So, but for the most part, I think you agree then. I don't know if heat conduction is really important or.
All right, well, why don't we stop there to give everybody a chance to go to the bathroom and whatnot. So we will be back at